Okay, so for our second talk of the session, we're delighted to have Po-Shen from King's College London, who's going to tell us about generalized symmetry and quantum computation.
So I would like to thank the organizers for the invitation to speak here. So I'm going to talk about a slightly different topic, but it also illustrates how to use symmetry to solve some problem in physics. So I'm going to talk about how generalized symmetry can apply in quantum computation. And this is based on a serious work I've done with lots of excellent collaborators, including Mason Brad-Cashley, who is going to be here, I think, and Ryohei Kobayashi, who is a postdoc in Maryland, and he's moving to IAS, and also going to IBM. And also some earlier works with Alex Truzio, who is in Parameter, and also Xie Chen, I think she's here, Apidua, Zhongming Jian, and Chen Kexu. Okay, so let me give you some motivation and early history of quantum computing. So basically, the motivation of quantum computing is the quantum advantage. Namely, for certain problems, quantum computer can solve it like exponentially faster than classical computers. So they have many potential applications, such as in quantum chemistry, like in new drug discovery, and also in like new encryption method in finance transaction. And quantum computers are prone to errors, so we need some kind of error correcting schemes. And the first error correcting quantum codes was invented by Peter Shor in 1994. And later on, Kitaev discovered the Tori code, which is related to finite group gauge theory. And the essential idea of quantum computing is to replace the classical bits, so like 0 and 1, by quantum states, so like 0 by some states and 1 by some orthogonal states. And the gates are operator acting on those quantum states. It can act on single, multiple qubits. So the basic idea of quantum computing is to encode the logical qubit as ground state wave functions of some gap lattice models of many physical qubits. And because there's a gap, so if you perturb the system a little bit, the ground state wave function still remain invariant. So there's some kind of robustness because of the energy gap. And as I suggested earlier, so because logical qubits are like ground state wave function, so if you have new quantum codes, they will describe new gap phases of matter, such as fractons or like higher dimensional topological orders. Okay. So one important thing is symmetry. So emergent symmetries of lattice model can preserve the space of ground states. And because the logical qubits are described by the ground state wave function, so they are the logical gates acting on the logical qubits. So one example is that suppose you have two copies of some gap lattice model, and you have a swap gate that just exchange the ground state wave functions of these two gap lattice model by exchanging everything in those two models. But you can also perturb one of the models just a little bit while preserving the ground state wave function. So this kind of symmetry, like exchange swap symmetry, becomes an emergent symmetry, but it's still a logical gate in this two copies of model. Now, it's important for the logical gate to be fault tolerant. And it means that suppose we have some errors or excitations that bring us out of the ground state, and after we apply the logical gate, the error or the excitation shouldn't shouldn't spread too much. So it means that we want the symmetry to be locality preserving. For instance, the symmetry can be on-site symmetry. Then we have a transversal logical gate, or more generally, it can be like finite depth local unitary or quantum cellular automata. So there are some challenges in finding fault-tolerant logical gates in quantum computers. So first of all, it's desirable to be able to apply the logical gate like simultaneously in parallel on different logical qubits. And another challenge is to have a logical gate that can realize a non-Clifford operation on the logical qubit. So Clifford groups are like generated by the Pauli operators. And if you want to realize all the possible like quantum computation, then you need non-Clifford. You need to realize non-Clifford operation on your logical qubit. And today I'm going to tell you how to use generalized symmetry to solve those two problems. And well, let me give you like other motivations to study this problem in physics and mathematics. So as I mentioned earlier, new quantum codes are basically new phases matter, so like fractons. And so for instance, the Kita code describes the Z2 gauge theory, which can also describe the low energy physics of a like S-wave superconductor where the U1 electron multisun is broken to Z2 by the condensation Cooper pair. And also the symmetries and anomalies of a quantum system, or namely the logical gates, which are the symmetries, and their computation relations, namely their anomalies, can constrain the aerodynamics. So for instance, suppose we can ask the question, suppose we know all the like logical gates and commutator, can it arise as an RG endpoint of some complicated UV model? So we can constrain this kind of RG flow by symmetry. Another important thing is that quantum codes can realize higher dimensional topological order even beyond the physical, like 3+1D dimension, using a long-range connection. So the idea is that suppose you have a cube, you can sort of like press it down to 2 dimensions, but there's some like long-range connection. So in this way, the quantum codes can realize like higher dimensional topological order. And quantum codes can also help us understand like higher fusion category, which describe all those higher dimensional topological orders, such as higher fusion category, and can also understand like some framework beyond topological orders, such as beyond the topological quantum field theory, like fractons. Okay. So for instance, we discover self-correcting quantum memories that correspond to non-abelian topological orders that do not have any particle excitation. Okay, so this is going to be the outline of my talk. So first I'm going to mention like what's the advantage of using high-frequency symmetry to provide logical gates in the quantum system. And I'm going to focus on a particular class of symmetry or particular class of logical gates, which is called the gauge SPD symmetry. And I'm going to illustrate this logical gates using various examples, like such as copies of Z2 gauge theory. In particular, I'm going to show that this class of symmetry can provide you non-Clifford gates, and also it can provide some new structure in higher fusion category. And in the end, if I have time, I'm going to say that by gauging those generalized symmetry, we can produce some non-abelian topological order without particles. So how do we apply a zero-form symmetry in the lattice model? So the idea is we can sweep the symmetry defect. So imagine you apply the symmetry in some finite region. Let's see. Yeah, imagine, in some finite region R. I'm not sure if you can see the cursor. And then, so there will be an excitation on the boundary of R, and those are the symmetry defect. And then imagine you grow this region where you apply the symmetry. So you sort of sweep the symmetry defect across the entire space. So in this way, you apply the zero-form symmetry on the entire system. Now in this talk, I'm going to focus on the quantum codes that describe finite group gauge theory. So the ground states are labeled by the holonomy on like different one cycles. And because this kind of sweeping is over the entire space, so this kind of zero-form symmetry will act on all the logical qubits, because you will sweep the like all the possible one cycles in space. So it means that this kind of the logical gates for this kind of zero-form symmetry must act on all the logical qubits at the same time, so it cannot act on different logical qubits or act on like logical qubits in parallel. And as you might anticipate, so this kind of problem can be solved if you consider high-frequency symmetry. So high-frequency symmetry means that you don't apply the symmetry on the entire space, but only on some like submanifold. So similarly, you can apply the high-frequency symmetry by sweeping the symmetry defect on some closed like higher codimension submanifold in space. So in this way, the logical gates of this high-frequency symmetry will only act on the logical qubits for the cycles that is wrapped by the support of the high-frequency symmetry. So we can apply this kind of logical gates in parallel. Another important benefit is that because we can choose like where we want to put the submanifold that has this high-frequency symmetry, so we can choose different topology of the support of the high-frequency symmetry. And in general, different topology will give you different logical gates. So this allows you to have a more versatile logical gate. Now, in this talk, I'm going to focus on invertible symmetry. So I will briefly mention non-invertible symmetry in the end. And so this invertible symmetries correspond to a unitary, well, I'm going to focus on unitary invertible symmetry. So they correspond to unitary logical gates in quantum codes. So invertible means that the symmetry defect, so let me call the symmetry defect A, you will have an inverse defect, such that if you put this A and the inverse defect A bar together, they can together be annihilated by a finite depth circuit to the trivial one. And one important advantage of invertible symmetry is that you can implement the symmetry operator using a finite depth circuit. So and the reason is you can nucleate like small strip of invertible symmetry defect. So there's yeah, it stopped working.
Nice. Okay. Yeah. Get another one. Right today. Okay, let's try this. Oops. Doesn't work. Okay. That's how it works. Okay.
Thanks. Yeah, sorry for the. There's no pointer. Okay, I can see. Okay. Anyway, so the idea is that you nucleate many strips of the invertible symmetry defect, like many strips of A and A bar, and then you pair annihilate the neighboring A and A bar. So like in this, well, I'm not sure who can see this darker region. Like you can pair annihilate A and A bar by a finite depth circuit. And in this way, you can use a finite depth circuit to move like one symmetry defect on the far left to the other symmetry defect on the far right using a finite depth circuit. Okay. So because I'm going to talk about copies of Z tutorial code, so let me just briefly, yeah, go ahead.
Mark the laser pointer.
Oh, that'd be great. Okay, thanks. Let me see. Okay, so thanks. Right, so let me just briefly review the tutorial code and just set the convention I'm using. So I'm going to put qubits on every edge, because that will be my Z2 gauge field. And the qubit is acted by poly operators like poly X and poly Z. And I'm going to call the gauge field my poly Z. So the gauge field can be 0 or 1 on each edge. And that corresponds to poly Z has eigenvalue +1, -1. And poly X will be my electric field. And the Hamiltonian will have two terms. So one term implements the Gauss law, the other implements the Flood condition of the gauge field. And suppose I consider the toric on a torus, because there are two independent one cycles, so there are two independent logical qubits. Okay, so what are the symmetries? Well, so one symmetry is the Wilson line operator, which is part of Z along the string where you put the Wilson line. Another symmetry is generated by the magnetic line operator, which is part of X for edges that cut the one cycle on the dual lattice. And because of the non-trivial computation relation between the X and Z, this magnetic operator actually implement the poly X gate. So here my convention is that if I put a bar, it means that the operator is acting on logical qubit. Okay. So the Wilson line corresponds to the poly Z gate. It tells you where the holonomy on this one cycle is +1 or -1. And the magnetic operator is the poly X gate. Okay. So, but there are way more symmetry other than the symmetry I just told you. And I'm going to focus on a particular class of symmetry called the gauge SPD symmetry. So SPD phases are like short-range integral phases with G symmetry, and can be described by some classical response action in the presence of the symmetry defect. And the way I define such symmetry is the following. So I can insert an operator that generates the gauge SPD symmetry by modifying the path integral of the G gauge field by additional weight. And the weight is given by evaluating this SPD partition function on some submanifold. Alternatively, I can define this operator lattice. So on the lattice, we can label the Hilbert space by the gauge field configuration on each edge. And then the operator that generates this SPD symmetry was just given by evaluating the SPD partition function for this gauge field configuration on this submanifold. Okay. And because the SPTs are described by the classical action, so they all have trivial braiding or trivial cohesion function. Okay. So how do we know the logical gauge for low symmetry? Well, the answer is straightforward because we just need to evaluate the SPT partition function for the holonomic configuration in the ground state. But sometimes this partition function is very complicated to compute. And another way to infer the logical gauge is using a computation relation. So as I said earlier, this SPT operator have trivial cohesion function. So to find non-trivial computation relation, we need to consider the commutator of the SPT symmetry operator with some other operator, which is the monadic operator. So the idea is that suppose you have a monadic operator as shown in this red. So you are carrying some holonomy. And to figure out what's the computation relation, we can wrap the SPT operator like in this way. Like we can sort of shrink this circle that wrap the monadic operator. And because the SPT operator is topological, so we can deform it in this way whenever the SPT operator intersects with the monadic operator. And then we will the monadic operator decorated with additional SPT operator, which is given by the twisted dimension reduction of the original SPT action on a circle with this particular holonomy prescribed by the monadic operator. So we have this kind of computation relation. So this computation relation in general describes symmetry. The reason is that we start with this SPT operator and the monadic operator, but we end up with a new operator that has one dimension lower compared to the original SPT operator. So it means that this computation relation output an operator that generates a higher form symmetry compared to the original SPT operator. And if the SPT phases are described by good cohomology, then this new lower dimensional SPT phase after the twisted dimension reduction is just given by the stem product. Okay, so let me just give you some example. So let's consider copies of Z2 gauge theory. So let me I'm going to call the gauge field a small a. So this superscript I labels which gauge field I'm talking about. The holonomy of the ith gauge field is the poly Z gauge for this I species qubit, logical qubit. So first of all, I mean, the basic gauge SPT symmetry is the SPT in 0 + 1 dimension, which is there is nothing but the Wilson line, so it gives you the poly Z gate. And the SPT in 1 + 1 dimension, if you have two Z2s, it is this A1 cup A2. So it tells you that on the boundary of this SPT, the two Z2s will anti-commute. And so what is the logical gate of this SPT symmetry? Well, let's try to evaluate the partition function for a general holonomic configuration. And this partition function is only non-trivial if both the gauge field, like A1 and A2, takes value 1 instead of 0. So it means that we have a control Z gate for the two logical qubits. And another way to see this is a control Z gate is by this computation relation like I mentioned earlier. So imagine you want to compute a computation relation between this gauge SPT operator and some monadic operator that create holonomy for the first Z2. So what I need to do is to reduce the SPT on a circle with a holonomy for the first Z2, but that will give you the Wilson line of the second Z2. So we have this computation relation, and which is indeed satisfied by the control Z operator. So let me also mention that the type of logical gate can be different from the constituent physical gate. So let's say we do not have multiple copies of Z2, we just have a single copy. And we can consider this particular SPT for a single Z2. This is the Lavangu phase. So we can ask what's the logical gates joined by this particular symmetry. Now, before that, let's try to ask what's the physical gate for the symmetry, and you can express it in terms of this control S gate. And in fact, the logical gates for this particular symmetry is different from like any of the constituent physical gates, and it also depends on the topology of the support. So if the topology is like free torus, then logical gate is actually trivial. If the support is RP3, logical gate is probably Z, and if the support is RP2 times S1, you actually got a control Z gate. So the support, so the type of logical gates is different from the, in general, different from the type of the constituent physical gates and depends on the topology. Okay. So let me talk about another example, which is Z2 gate theory with fermionic electric charge. So the fermion is an emergent fermion. And let's ask what's the symmetry of the theory. So first of all, there's a one-form symmetry generated by the magnetic membrane operator. And there are also various gauge SPD symmetry correspond to the fermion SPD phases in different dimensions. So for instance, there's Wilson line. There's also a membrane operator decorated with the Kitov-Chen phase. There's also a domain wall operator decorated by the P plus IP. Okay. So what's the symmetry generated by those operators? And it turns out that the symmetry it can be different from the classification of the fermionic SPD phase. And the reason is that some of the gauge SPD operator do not act faithfully on the ground state. So, for instance, if the P plus the symmetry, the classification of SPT generated by P plus IP is integer, molecular central charge, but it only depends on the holonomy of the ground state or the spin structure by ZA. So we have this kind of symmetry reduction. Okay. So how does the symmetry act on the system? So the domain wall decorated with the P plus IP actually implements a permutation action on the Z2 times Z2 one-function symmetry. So one of the Z2 is generated by a multi-operator. The other Z2 is generated by the Kitov-Chen operator. So the idea is that if you have a multi-operator that intersect with the P plus IP domain wall, you'll create a vortex, and the vortex has a marginal zero mole. And the marginal zero mole lives on the boundary of the Kitov-Chen, so you have this kind of configuration. So after it pierces the P plus IP domain wall, it becomes some kind of dynamic operator decorated with additional Kitov-Chen phase. And this kind of configuration can also be inferred by the twisted dimension reduction I mentioned earlier. So we have this kind of computation relation. So let me mention another thing. So it's important to understand not just the fusion rule of a symmetry operator, but also it's a associator. So let's consider this kind of fusion configuration. So we have this P plus IP wall, and we have two multi-flux here. And after it pierces the wall, it becomes some kind of dynamic operator with additional Kitov-Chen. So we can consider these two different fusion configurations with the same external configuration. So at this intersection point, we have a vortex sigma. But we can also first fuse the multi-flux, namely we can fuse these two vortex. But fusion of two sigma will give you 1 plus psi. So psi is the electric charge. 1 plus psi can freely move to the bulk. So it means that the two fusion configurations differ by 1 plus the Wilson line in this Z2 gauge theory with fermionic charge. So it means that this symmetries actually have a very non-trivial associators. 1 plus psi is it generates a non-vertible symmetry. It means that this symmetry actually have a associator that takes value in non-vertible symmetry. Okay. So let me just quickly mention that we can ask what are the logical gates for the symmetry. And for the membrane operator decorated with Kitov-Chen, we can get a control Z gate or the S gate. Well, for the domain wall decorated with P plus IP, you can get a control Z, control S, or the T gate, which are non-free-flow gates that are important for universal quantum computing. And let me also mention that we can repeat the same discussion, not just for a Z2 one-phone gauge theory, but for Z2 higher phone gauge theory. So for instance, if you have two Z2 higher phone gauge field we can consider a gauge SPT symmetry for this kind of Po-Shen function or effective action. And if we gauge this gauge SPT symmetry, we actually end up with a non-abelian logical order. And the reason is that after we gauge this symmetry, the twist effect or the multi-vortex will live on the boundary of this SPT, and it will carry projective presentation. And therefore, the vortex will become non-abelian. So you obey this kind of fusion rule, where M is the vortex and WA and WB are the Wilson operators for A and B. And you can choose the degree of the gauging in a suitable way, such that there are no particles in the theory. And it turns out that the minimal space-time dimension has to be 6. And actually, this is actually a general requirement for this kind of theory. And we also construct a non-Pauli stabilizer lattice model for the theory. And because the theory does not have particles, it's a self-correcting quantum memory. Okay, so let me conclude. Yeah. So in this talk, I'm trying to show you that using generalized symmetry, such as higher group symmetry, higher function symmetry, it can provide new applications in quantum computation, such as new logical gates or a new non-abelian self-correcting quantum memory. And we illustrate this idea by studying the gauge SPT symmetry in various examples that can give you new logical control Z, control S, and also new non-Clifford gates. And we also discovered new structure in fusion 3 category. So remember, there is some new associator that takes value in non-vertible symmetry. And by gauging the generalized symmetry, we can obtain non-abelian self-correcting quantum memory. So let me stop here. Thank you. Sorry for going over time.
Thanks very much. I see there are already lots of questions. So.
Yeah, when you gauge this SPT symmetry, what kind of theory do you get? Do you get some kind of higher gauge theory in general?
It can be expressed as higher gauge theory, but objectively you will have some. You can have, for instance, in the simpler example, you have a abelian loop excitation and non-abelian membrane excitation.
I see. So maybe that's generally true. That's you always get a some kind of higher.
Yeah, it can be expressed as a higher.
But then there's the higher gauge theory always have some particle-like excitation. So
not necessarily.
I see. There's certain. Yeah. I see. So you say there's certain higher gauge theory don't.
Yeah, there's some certain. Yeah.
It does happen in 3+1 dimension.
No, the minimal dimension where you don't have particle is 5+1D.
Oh, okay. Yeah. Thank you.
5+1D and above.
Yeah, that's my confusion. Yes, thank you.
There's another question.
Thank you for the talk. My question is, what do you think is the limiting factor of finding ways to combine a universal gate set from these logical gates? So, for example, does higher symmetries, does that give you a way to find new gauge fixing or subsystem codes? And
yeah, I mean, there are certainly many things to explore. Like maybe you can explore new applications of subsystem code, or yeah. I mean, it's part of work in progress, but I would say it's very exciting application for generalized symmetries that people should look at.
Sorry, I asked about. Sorry, I'll clarify. I asked about the limiting factors. Do you think it's a kind of computational issue or some theory we don't understand, or is it hard to find Hamiltonians and materials or naturally that?
I guess it's combination. For instance, you can ask the question like what kind of fusion, like what kind of symmetry can give you universal gate, for instance. So I mean, there are both conceptual issue, like theoretical issue, and also I mean, how to write down a lattice Hamiltonian for that, for all those specs. Yeah.
Thank you so much.
So in the fusion 3 category, the associator that you're computing, that defect is a condensation defect of the lower dimension.
Yeah, it's a condensation defect of lower dimension. Yeah.
So I guess in principle, even though it's very hard, to compute all the data, we just input the data of the lower dimensional operator. So that's why the associator is fixed by the...
Yeah, I mean, yeah, maybe there are some more general example where the associator is not just this condensation defect, but maybe there are more non-trivial associator. Okay. I don't have an example it'll be interesting to look at.
Thank you.
Thanks. So, as a follow-up to that question, actually, so just very basically, when you say the associator of your Fusion 3 category, what level?
I mean, when I say associator, I have to put like quotation mark because usually associator means just a number, like complex number, right? So in this case, people will say this category is just non-associative because there's non-trivial operator for these two Fusion configurations.
I see. I was just curious at what level of the 3 category you're talking about when you say associator.
Oh, right. So the 3 category has, so for instance, it has topological line, topological surface, and topological domain wall. So they will describe some Fusion 3 category.
But what level is the associator living on? That's what I'm.
What level? Well, I mean, this is the associator I'm talking about for fusing this magnetic membrane operator with this domain wall operator. So these two fusion configurations differ by a non-trivial operator. So that's the associator I'm talking about.
I see. Okay, thanks.
Any question?
So when you compute these commutation rules with the magnetic flux, so I think in some theories, not the ones you're looking at, but the magnetic flux can be a dynamical thing, like not topological operator, like Google operators. You still have some analog of this, I guess, no? Did you?
Yeah, I mean, you can still have some like OPE, right? I mean, as long as the domain wall is topological, we can talk about its action on some non-topological operators.
But you know to characterize it for this, how did you call them, gauged difference?
Yeah, so for instance, you can couple the Z2 gauge theory to some matter, then the magnetic operator will be non-topological, but you can still have this kind of symmetry because the P plus IP wall is still topological.
You will get the same formula.
It is the same, yeah.
Okay.
Yeah.
Okay, there are no more questions. Let's thank Po-Shen, first of all, for his nice talk. This is our first lunch break, so you all have a booklet. If you don't have it, take one from the front. It has all kinds of suggestions for lunch options. My personal recommendation today only, you have the Japanese truck outside. If you like Japanese food, just go there. Maybe not all of you, but some of them. And the maps should be, also you should be able to scan in the QR codes and the maps will lead you to all the places. There's also an announcement for all the people doing a gong show. Could maybe just stick around and then talk to them. Come all to the front just now, and we'll see you in the afternoon.